Okay, welcome back. Remember I told you that today I expect that we're going to be interrupted, right? That at some point someone's going to walk in and start pulling people out of the classroom and, I don't know, torturing you or something. I don't know what they're going to do. But I went online this morning around, I don't know, 20, 30 minutes ago. Philip Campbell, Kevin, is that Foyles? Kevin, is Kevin here? Okay, is it Brinian Green? Is Brinian here? No? Justin Guerrero? Okay, Justin, Gina Nicholson, and Jonathan Jackson. Okay, the names I called are the people who have not completed the quiz online that is supposed to be done, that says that you have read the syllabus, you've watched the orientation video, and you understand the requirements of the course. Everybody else did it, okay? So if I called your name, you've got to get up to speed. What's going on, okay? If you don't know what I'm talking about, go into Canvas, take a look. You got to take the initiative on that. And now I hand it over to my colleague here. Go ahead.
Basically, I'm going to talk to each of you for just a few moments about your math placement. Everybody has tested in or has taken prerequisite to get into 1414, but one of the things we found out is that sometimes students may or may not be ready for 1414, and we want to make sure that you're in the right place. We want to make sure that this is a good fit for you. If you feel like you might be lost in here, it might benefit you and save you a little bit of time if we can find you a better spot. So my job is not to convince you to drop this course. My job is not to convince you to stay in here. My job is to make sure that
Just come over here.
you've got the right
Slide down a little bit.
So,
We can join these up together, okay?
Robert, did they have something they worked on from last time?
Well, they started the packet. The packet was due today, right?
They still have it?
They should, because they're going to be turning it in, so.
Okay.
Yeah.
So what I would like you guys to do, I'm going to have you just come out one at a time. I'll probably just go table by table. I'll talk to you, and then when you're done, you come in to the next person. Bring the packet with you. So when you come out, bring that packet with you. We'll look it over real quick, and I'm going to try to give you guys the best advising that I can.
Good. Take your first victim. Okay, so look, this is not a grade, okay? This is not like he's going to go out there and be like, you know, F, because you don't have the packet done, all right? You just go out there, and I don't want people scrambling now to try and finish the packet so that when you get out there, it looks like you did it. The point is you should have had it completed by the time you walked in here today, right? And if you were able to do it, then you're probably ready for this class. If you tried it and you really struggled with it, then the idea is that you're not prepared for this class. So there's no sense in you sitting here, you know, suffering for 16 weeks or whatever just to have the inevitable happen, which is that you don't get through the class. Does that make sense? This is for you. It's not for us, not to try and make this harder for you. Now, if you go out there and you say, hey, look, I mean, I feel like I can do this math. It just wasn't enough time. You talk to him about that. Nobody's going to force you to do anything today. It's advising, okay? So even if you have no idea what you're doing and you didn't try it all on it, but you still want to stay in the class, I can't force you to leave the class. I can't. He can't. I can't. All right? So you make the decision that's right for you. All right? Now, I do want to talk a little bit about, I think this is too bright. Too much sun. I do want to talk about the videos that I'm going to be making. I've decided what I'll be doing is I'm going to be recording using that camera. And see those little black lines up there? I've got to stay within those lines while I lecture. So I'm going to write stuff down, then I'll erase it and write down. So I'm always going to stay right there. I've got a microphone. The audio comes out pretty good. So I want to show you what it looks like so that you'll be able to go back and look at it. Everybody knows that they can log into Canvas. Server busy. Never mind, you can't log into Canvas apparently. Try it one more time. Okay, so instead I'm going to go to YouTube because all your videos will be contained on YouTube. And in Canvas there's a link to these videos. Right? In your Canvas homepage there's a link to these. But if you want to get to it right through YouTube, just go to YouTube, type in Robert Math Guy, and you'll see this little image. Nathan? Right, Nathan? Do you mind killing the lights? Maybe just yeah, that's perfect. Okay. So if you just go here and you can get to my playlist somehow. Playlists. Where do I have the option for playlist? Sorry, I'm not seeing it.
The second row of videos.
I'm used to seeing it in the manager's view, so I'm not used to seeing it this way.
But you do see it, right?
No, I do not. Oh, created playlist. There you go, there. I thought you were saying create a playlist. Okay, yes.
Second row of videos.
Sorry. All right. All right. So here are all my playlists, and I have stuff from the past, and you can actually go back, and there are some 1414 videos from last semester that you can watch, but I used to use a different sort of style, and what I did was I used a tablet, and let me just bring this up here, and so you can't hear, oh there you go, you can hear it. So I'm talking and I'm writing and everything is here, but I'm not actually in the picture. It's just always going to be just that screen. That's the way I used to do it, and I went away from that this semester. And so my Cal 2 class yesterday, this is what your video will look like. So I just wanted to point out a couple of things on this video. When you're watching a video on YouTube, you can go over here to settings, this little gear, and you can change the resolution, and it just depends on the speed of your internet at home. 720p is the best resolution you can get. And notice the little gear wheel is turning now. And then once it stops turning, it's going to say it's in HD, and I'm going to go to full screen. Give it a second to catch up. There we go, we're in HD, so. And then you can hear me talking. So that's about the best resolution you're going to get, but I think it's pretty darn good considering, you know, what it is, right? It's streaming, and so there should be no problems being able to see what I'm writing down and being able to go back and watch it. All right? That is not a substitute for coming to class. You still have to come to class, but the idea is that you can sit there and during class you can pay a little bit more attention to what I'm saying and what I'm doing, rather than focusing so much on writing everything down, because you'll be able to get to it later. Understand? All right, so let's see. Here's Kevin, you want your thing? All right. So, let me hand back your first quiz, because I said I wanted to give these back to you, right? Let's see, Jordan. But you know, let me pass it around. You just pull yours out. This was that group thing you did last time. So just pull yours out and then pass the stack around. I read all of them. Some of them were kind of entertaining. In particular, David's yours was the most entertaining. I believe it was you. When I asked what the qualities of a good student, was that you that answered? Did I write a little note next to it? Okay, so what are we doing today? We were going to continue on the review, right? But I figured you would have some questions about the packet. So do you want to talk about the packet at all? Because maybe you tried it and there were just a few that caused some issues. Anything off the packet?
16 through 18.
16 through 18. So I don't have a copy of the packet, so I'm going to have to ask for someone to, what is this? You got extra here? Okay, 16 through 18. Quadratics. All right, so let's go for this. You want me to do, let me do 16 first. Here we go. You ready? I'm gonna call you out and check you off as being here. All right, I'm just going to go in a random order here. So how about Angie? Is Angie here? Angie? Yes, Angie. Hi, Angie. Did you try this problem, Angie?
Yeah.
You did? Any particular success with it?
I don't know if I do it, but
Okay, can you tell me at least what you tried to do?
I moved from 50 to the other side.
You moved it to the other side, and that's the standard approach because it's a quadratic equation. And when you have quadratic equations, we know that because it has x squared, you always want to try and isolate, basically get 0 on one side. All right? That's what we do generally. Sometimes you can get around that and not have to do that. But in this case, because there are 3 terms, you can move the 1/5 to the left side, which would create a negative 1/5. Yes? Okay, good, Angie. How about Michael Carter? Where's Michael Carter? Hey, did you try this one, Michael? Okay, so what did you do? Did you move the 1/5 over? Okay, so what do you do after that? What did you do? Okay, so you actually created a common denominator, or you found what an LCD was, right? You found one in what, 15? What did you do with that 15? Did you like rewrite this as something over 15, something over 15, something over 15? Yes? That is actually a way you can do it. It's not the only way, though. Did anybody find a common denominator and multiply both sides by the common denominator? Yes? That would work also. That's called clearing fractions. So let's take a vote because both of those ways would work. How many of you would get a 15 underneath everything and work with it like that? Yes? How many of you got a 15 and multiplied through? That's about the same. How many of you are lost already? Yeah? Okay. What did you do? Quadratic formula, absolutely. That'll always work, right? So you could do that also. So we have all these different things that we could have done. And the idea here is that because it's a take-home assignment is that you just have to figure it out. You have to use a technique that works. And there appears to be 3 or 4 different ways of doing this. Now, here's why I would avoid quadratic formula if I were doing this. Only because I have fractions right now. And because I have fractions, a quadratic formula could get a little bit messy. I would always want to clear my fractions first. So let me do it the way that I would do it. I know a few of you would, and that's clearing fractions first. So what I'm going to do is I'm going to find the least common denominator between those 2 denominators, 3 and 5. So what's the LCD there? 15. And then I'm going to use that number, and because it's an equation, I'm going to multiply everything by 15, both sides. So I'm going to put a 15 over here. And of course, 15 times 0 on the right side doesn't do anything, right? Still stays 0. But watch what happens on the left. This should have the effect of getting rid of all fractions when I distribute this 15 through to each term. So what's 15 times 1/3? That's 5, right? So you're basically taking 15, you're dividing by the 3, that gives you 5. So you have 5x squareds. And then you do 15 times negative 2x, but the negative 2 times the 15 gives you negative 30. So you have negative 30 x's. And then the 15 times the negative 1/5, the 5 divides into the 15 3 times, so you get negative 3. Okay? So you have minus 3, and then we said the right side was 0. So all we've done is transform the quadratic equation that had fractions into a quadratic equation that no longer has fractions. And that's just easier to work with. Now at this point, you kind of have a few choices. You can try and factor it, or you can try the quadratic formula. And I heard Nathan say factoring may not work. In this case, you tried it, it doesn't work? No. So, but let's check it just to make sure, because factoring is a technique that everyone here needs to know how to do. If I was trying to factor this left side, I would take the number in front, 5. I'd multiply it times the number in the back, which is -3, and that would give me -15, right? And then, how many of you have seen that before? Something like that? No? Or do you have a method, something similar to this? Okay, it's like, this is called the AC method. So I take the -15, and then what number do I put here? The number in front of the x term, -30. And you have to come up with two numbers, question marks here, two numbers that multiply to be -15, add up to be -30. So they have to multiply to be this and add to be this. And it's not going to happen, right? It's not happening. Here's another example of if we had something like this, what numbers could we use here? I got you, didn't I? 2 and 3, right? 2 and 3 multiply to be 6. 2 and 3 add up to be 5. Now you could not do 1 in, or -1 and 6, because then they would multiply to be -6. So that mess with the numbers. But that's the idea here. We're trying to come up with two numbers that multiply to be 6 and add to be 5. Here we cannot figure out, there's no numbers that do that. So since we cannot use this method, we don't say that it is prime, or we don't say it's not factorable. We pull out the quadratic formula and we hope for the best. So the quadratic formula, hopefully you've seen, and of course you have it memorized by now, right? No, maybe not. It says that if you're given a quadratic equation that looks like that, the solutions to this equation are always guaranteed to exist, and that will always be, or always come from this formula right here. Very, very nice, powerful formula. We just have to identify the pieces of that formula and just plug in. So this is what we refer to as like a plug and chug. You just find the numbers, you plug them in, you chug out the answer, you're done. That's it. So what are our numbers? What's A for us in our problem? 5. What's B for us? -30. And C is -3. So just make sure you keep track of the signs. And then I plug into that formula. X is equal to, what's -B? It's the opposite of what I have. +30. Plus or minus the square root of, B squared. So -30 times -30 is 900. Minus 4 times A times C, -3, right? And then all of this divided by 2 times 5, which will be 10, right? So that's just plugging everything in. The trickiest part of this, in my experience, the trickiest part has always been this part. People will mess this up. And so there's different ways to look at it. Again, I'm not really here to reteach this. You should know this already, but we're revisiting it. One way you could do it is, if you look at the signs of the three numbers, you have what? Negative, positive, negative. What happens if you take a negative, a positive, and a negative and multiply them together? What would you get? You get a positive, because you have two negatives in there, right? So that means that you're going to have the 900, and then you're going to have a plus sign. Okay, and then just take the numbers and multiply them together. What are they? 60. So you have 30 plus or minus square root of 900, and then plus 60, and then over 10. And be careful with this 2 times 5, this 10 down here. This 10, this division bar goes all the way across. It does not divide into that root. You are not allowed to touch that root, what's underneath it, the radicand. You can't touch it with this 10. You can't. Because that 10 has an effect on the 30 also. So leave that 10 there. 900 plus 60 is 960. And I suppose we could take that as an answer. unless 960 is a perfect square and it breaks down nice, that's not a perfect square, is it, right?
No.
But you could probably do something with it. 960, you could probably like factor 960 out and take a perfect square out. Did anyone go further with 960? Yes? Do you get anything? See, Aaron, you shook your head yes.
I got a square root of x equals 30 plus or minus 8 square root of 15.
8 square root of 15. So you were able to figure out that 960 breaks down to be 64 times 15? Is that what you were able to?
I did it 2 divided by 2 divided by
Yeah, so you did that over and over, but basically you figured out that if you take 960, it is 64 times 15. Right? And then what happens is you take the square root, that means you're taking the square root of 64 and the square root of 15 separately. What's the square root of 64? 8. And then square root of 15 is just square root of 15. I'm trusting Aaron's work. Is that, y'all okay with that? Do I need to break a calculator out and check Aaron or no? Seems right? Okay. Let's see. 8 and then root 15. I hear people getting their calculators out. I guess they don't trust you, Aaron. Okay, well, at least you're honest. I wouldn't trust me either. All right, let's do it. 64 times 15 is 960. Okay. So I guess what I'm getting at is I would take this on a test, okay? And if you have that on your paper, I would take that also. But we need to be comfortable going further. At this point, is there anything else I can do?
You can divide it by
The 10, I can actually work with the 10 now? Yes? What I can do is I can look at the numbers 30, 8, and 10 and see if there's a number that goes into all of them. 2? So I can reduce all those by a factor of 2. But this 15 is stuck. You don't touch it, all right? So let's reduce everything by a factor of 2. We got 15 plus or minus 4 root 15, all of this divided by 5. And I'd say that's probably where we want to go. That's the exact answer. And there's actually 2 answers, aren't there?
Yes.
There's 2 of them. There's the 15 plus this number, then divide that by 5, or 15 minus this number, and then divide that by 5. And we want to be able to do that decimal on our calculator. Yes?
Would you want that in set notation or?
I'm not sure what you mean by set notation.
Or the little squiggly bracket thing?
The braces around it? No, not necessarily. You could, as long as you have x equals that, we're okay. You do need to realize that this represents 2 numbers, right?
Wow.
That's all. So the braces do that.
Last class you did it and you listed both of them.
Yeah, you would do something like this. 15 plus 4 root 15 over 5, and then the other answer is 15 minus 4 root 15 over 5. The braces mean these are individual answers, and here they are.
And that's what you want? Or
I would take this. This is fine.
Did you say you would also accept it in decimal form?
I would accept it in decimal form, but you need to be able to do this, and then at this point go to decimal. Yeah. Not just type into your calculator, solve, because these calculators, some of them will solve the equation right off the bat. No work. You don't even have to do anything. Right? So. Which then brings up a bigger question, like why do we do this if we can just go to a website and have it do it for us, right? There's an answer to that question, but maybe we'll entertain that later. Okay, now that was, who asked this question? Okay, so Stephanie, does this in any way help you with 17 or 18? Yes? So you're okay with 17, getting 17 to turn into a quadratic first? Okay, I'll just run through that real quick with everyone so that we at least see it. So we have this equation, and we're trying to solve for x. The problem that we have here, it's not quadratic. When you look at it right away, this does not look like a quadratic equation, right? But you have your x appearing in a denominator, which does cause an issue. So we have to release the x from the denominator. And the way we can approach it is kind of like we did in the last problem. We didn't like the fractions, so we got rid of them, right? We came through with a 15. Here, we want to get the x out of the bottom, so we can do the same thing, multiply everything by x, though, instead of a number. So if I multiply the left side of this by x, and I multiply the right side by x, I'm going to put 2 in front of the x, and just see what happens. Maybe we can work with that afterward, right? So multiply the x through. What's x times 1 over x? They cancel out, so you're left with a 1. So it's important to remember, even though they cancel, you have a number there, it's 1. And then the next one, plus x squared, and then on the right side, 2x. And now you have a quadratic equation again, right? Now you'd move everything to one side and put it in descending order. So if I move everything to one side and put in descending order, what do I mean by descending order? Highest power of x down. So I just moved this over, which made it negative, and then just rearranged it, and that's it. Now it's a quadratic, right? So you could do the rest of this yourself. You're probably going to need the quadratic formula again, because I don't believe that factors. Yeah, it does. It does factor. It does factor. If you do your tree, this will be the easiest way to do it. The number in front times the number in back. The number in the middle. The two numbers that multiply to be this and add to be this are -1 and -1. -1 times -1 is 1. -1 plus -1 is -2. And so what you can do is you can determine that this factors this way. So how many solutions do you have here? You just have one. It's the same solution. We call that a repeated root or something like that. Okay. So there's some work that would have to happen to go from here up to this, okay? I'm putting a little asterisk star there. I mean, I'm trusting that you would be able to go through a process to get you there. All right. That should take care of 18, all right, also, because 18 is done the same way. Any others on here?
I don't know, I could get 8 for some reason. I don't know.
8? Okay. Did the packet of quizzes get around? Yes? Didn't get it here? Okay. Here you go. So number 8. X to the 4th plus 13x squared plus 36. Now the instructions here are different than the previous ones, right? The instructions here were to factor. So what's the difference between this problem and the one before when it says factor? Nathan's saying leaving factor form. Someone said something else. I didn't hear it. You're not solving for x? Why not?
Because it's just asking me a factor. It's not telling me to solve the.
It's not telling me to solve. It's saying factor. There's something else that tells me that I'm not solving. There's no equal sign. It's not an equation, right? This is an expression. There's a difference between an expression and an equation. If I had an equals in here, then I'd be trying to find solutions or something like that. If I don't have an equation, it's an expression. And that's important because the power of the equation is that you can multiply both sides of an equation by a number or add something both sides. When you have expressions, you can't just come in and arbitrarily multiply this by something. If you do that, you change the value of the expression, right? So like if I come in here and tell you, look, here's the number 4. You can't now say, oh, I'm going to multiply it by 2, and it's the same thing. It's not. It's now 8. That's not 4. If you have an equation, x is equal to 4, and I multiply both sides by 2, I get what? 2x equals 8. But that still means that x was 4. So it still maintains the equality. And so no equal sign, big difference. All right, so with that said, I have to factor this. And it gave you a hint to what? You may use U substitution. So this was just to make sure you understood or you had seen what U substitution is. U substitution is where we look at something like this and we say it kind of looks like something we're familiar with. If we just squint our eyes and look hard enough, it actually is something we've seen before. So how about if we rewrite this as x squared squared plus 13. I'm going to put this in parentheses even though I don't need to. Do you agree that that's the same exact expression? X squared squared is x to the fourth because you what? Add? Multiply those, right? 2 times 2 is 4. And then I just put x squared in parentheses here just to kind of help you see that if you step back from that, that x squared that's in parentheses, if I just came in here and made a substitution, that u was x squared. So everywhere I see an x squared, I want to replace it with a u. Then this turns into u squared plus 13u plus 36. Do you agree? And then from here, now it looks like something we're familiar with. This is a quadratic, right? This was not a quadratic. We call this a quadratic form because it kind of looks like a quadratic if you do this little game, play this game of substitution. So this is what we refer to as a quadratic in U, a quadratic in U, meaning that this is a quadratic. If U is the variable, this is a quadratic in U. This is not a quadratic in U. This is a 4th degree in X, right? 4th degree. So now we can do this thing. Can I use a quadratic formula here? It's tricky. You have to be careful. There are ways, and some instructors do use the quadratic formula to factor. But generally speaking, if you don't have an equation, you can't use a quadratic formula because the quadratic formula relies on the fact that you're trying to solve an equation, right? ax squared plus bx plus c equals 0. We don't have that here. But I can play this game. 36, 13. What is that? 9 and 4. Yeah, that works. And that means that this will factor to be what? The variable u plus 9 or minus 9. What is it? Plus, okay. U plus 4. And then at the end, you can't be done here because look, your original problem has x's, right? And you're saying that this is the answer. You'll see that doesn't make any sense, right? It's like me saying, what's your favorite color? And you're like, 13, you know? It's like, what's x here? You're like answering me and you have u in it. It doesn't. So just switch it back. All right, so replacing the u with x squared, we get x squared plus 9 and x squared plus 4. And now, is this completely factored? Yes? You'll agree? I can't break this down? I thought there was something if you had squared and squared you could. It's addition. You can't break that down, right? If this were subtraction, could it go further? Yes, it would be difference of squares. It would turn into two different things. But fortunately for us, it stopped. Yes?
Now, I got that exact same answer, but I've never heard that used in.
Okay.
Is that okay?
I was just about to say that. Some of you could just look at this and go straight to that.
I just factor.
And some of you can do it mentally, maybe. And if you're there, good. This is not designed to make your life more difficult, okay? It's designed, if you are struggling with this concept, here's an approach called U substitution. Is there?
Could you use the 18 method from the very beginning of the
Yes, you could. You just have to make sure you remember that it's not x here and x here. It's x squared and x squared. Yeah. Yep. But U substitution is something that is very, very useful to us. Whenever we have something that's extremely complicated, we can make a substitution replacing the complicated part by U, and then it looks much nicer. If you don't believe that, how many of you have to take Cal 2? Okay, Cal 2. In Cal 2, there's something called integration by substitution. And this is the basic idea. You look at something, you're like, oh man, this is really complicated. And then you say, hey, but if I look at it this way and call that u, then it gets a little nicer and I can work with it a little easier. So the actual method of substitution is something you should be comfortable with. All right, any other things? Yes?
Yeah, on this question,
Uh-huh.
I got x plus 3 squared and x plus 2 squared.
X,
Can you do that, or is
x
that
plus, oh, that's like, hold on, x plus, so you went further with this?
Yeah.
X plus 3.
Is that,
That's your, thank you.
is that also, can that be also the answer?
This is a wonderful question. Where's your name thing? You're Giovanna, right? All right, see, I don't need your name thing. Giovanna is asking this question. Are these equivalent? Because x squared is x squared and 3 squared is 9.
You're taking the two terms and multiplying them together, so you have to become x squared plus.
Yeah, when you say x plus 3 squared, that means x plus 3 times x plus 3, doesn't it?
Okay.
And then if you did the actual foiling of this, x times x would give you the x squared. Got that. Then you'd have what? 3x and then 3x. That's 6 x's. You don't have 6 x's up there. And 3 times 3 is 9. You have the 9. So you actually, you added stuff. By doing this, you added stuff in there. So I'm glad you asked, because we want to make sure that we are comfortable, because sometimes we try and do things because they look like they'd be right, but they're actually not. So just be careful. There's another one, something like this I see a lot. This is equal to x plus 3. It's not. Because what you're doing there is basically exactly what we did here. You're thinking that this power can go to each one. When there's addition there, you can't do that. And here what you're thinking is that this square root, which is a power, can go to each one. And that doesn't work. Whenever you get into a situation, I know when I was a student at this level, I was never a math prodigy as a kid or anything like that. I hated math, actually, for a long, long time. I would give myself problems to see if I could convince myself whether or not something was true or not, because I wasn't comfortable enough with it to be confident that I was doing it the right way. So something like this. If I'm sitting there and I'm thinking to myself, is this x plus 3? Well, one thing I could do is just check a number. Just plug a number in and see if it works. Like, what if I plug in 0 for x? What do you get? Square root of 9. Over here, you get, plugging in 0 for x. You get 3. Is the square root of 9 equal to 3? Yes? I'm not trying to trick you. So if I did that, I would feel pretty good that this is right. Yes? But just because it worked one time doesn't mean it's always going to work. So I doubly make sure by trying another number. So how about 1? If I plug in 1 here, what do you get? Square root of 10. Is that equal to 1 plus 3? Is that equal to 4? No, because I know that I would need this to be what? Square root of what is 4? 16. I would need that to be a 16. So even though it did work for 0, it's not working when I try and plug 1 in. So generally speaking, it's not equal. It's not equal all the time. It's conditionally equal. If x is 0, then it's equal. Understand? So if you ever run into issues like that, just try and plug things in and see if you get the same results. It's not guaranteed that it's going to work in your favor that way, but at least you'll feel more confident about it, right? What else?
Number 20.
20? I need your thing again. Let me just take a look. 25. Okay, so what was the problem with that?
Imaginary number.
Imaginary? What the hell is an imaginary number? We're going to talk more about this, all right? Imaginary number thing. So it does not factor with the AC method, right? It's not going to work. You can try it. So we go straight to the quadratic formula. And from the sounds of it, a lot of you sound like you probably got to this point already. What did you get under the root after you cleaned it all up? Negative 11? And down here, 10? For those of you who tried it, most of you got to that point? Yes? And this will all depend on your background. If you've seen imaginary numbers, then you know what you can do with that. If you haven't, then you're like, what's the square root of negative 11? Right? So we're going to investigate this more, but that would be okay if you just answered like that. But we will learn even more later that the square root of negative 11 can be written as what? I root 11. So let's do a vote here. How many of you have seen I before? Oh, wow, good. See, that's good. Okay, so what is I? Well, we're talking about it. What is I? It's the square root of negative 1. That's the definition of what I is. It is defined to be the number that when you square it, you get negative 1. Just like when we say 2 is the square root of 4, we're saying that 2, if I square it, I get what's underneath here, right? 2 squared is 4. 2 squared is 4. That's what this means. Over here, what this means is that I squared is what? Negative 1. Negative 1. Right? So historically what happened was, the numbers came about if you believe in this. It depends on your philosophy on the way things began. If you believe that people at some point had to try and start to count things, then what do you think the first number that we came up with was? 1, right? So our standard counting numbers were the first numbers that we figured out. And we figured out pretty early. When I say we, I'm talking about like humankind, okay? We started out with 1, then we went out, and then we realized that we needed more than just this. And there was a huge breakthrough. And I saw recently in a video or something like that, that it dates back, I don't know how far, but it was a farmer who came up with the idea of 0. The idea of nothing, having nothing, was a huge leap. Okay? And because if you're trying to count things like I will give you, 2 sheep for your 3 pigs, you're trying to survive. Let me give you 1 basket of berries and you give me 2 baskets of whatever the hell it is, right? And they're trading. You were never like, let me give you 0 of this and you give me 0 of that. They never needed 0. For a long time they didn't need it. But then they had to start, advancing, and so 0 came next. What do you think came after 0? The negative numbers. So now I know that if I take 1, it has an opposite number, right? Its opposite is negative 1. If I put those 2 together, what do I get? 0. So you couldn't have the negatives before you had 0, so 0 had to come first. And then these keep going, right? And if you look at a number line, here's what we have so far. We've got 0, we've got 1, we've got 2, keeps going that way. We've got negative 1, negative 2, right? So we're starting to get these dots. Double negative. Yeah, it's a double negative. Negative 1. There we go. So what do you think came next? After that? Fractions came next. Yep. So you realize that now that you can have something between 0 and 1, like 1/2. Right? So what happens if I start filling in all the fractions here? 1/2, how about 1/4, how about 3/4? How about if I fill in all the fractions? I'd be here forever, right? There's an infinite number of them?
Yes.
Would you agree with that?
Yes.
Okay. So here's a more profound question. If I fill in all the fractions, is it a solid line? What do you mean?
Solid.
You can't fill it.
What do you mean?
Because it's infinite amount.
I know, but I'm saying if there was a way that I could put all the fractions in there, do I have a solid line? Are there any gaps or holes? What do you think? So let me reverse that question. If I draw a solid line, which you all know is the number line, right? If I draw the solid line, and I go in here, I'm going to peek, hold on, and I grab a number, is it a fraction? Okay, so let's look at these numbers right here. Is 1 a fraction?
Yes, it is.
It's 1 over 1. Is 2 a fraction? 2 over 1. Is 3 a fraction? Sure. So all the numbers that we have here are fractions, aren't they? But then 1/2 is also a fraction. So if I grab that, there's my number. Is it a fraction? So two different questions, but they're asking kind of the same thing. So we're going to take a show of hands, and I'll be clear, make sure I'm clear, that you believe that if you put all the fractions on a number line, it creates a solid line. Or if you draw a solid line which represents all the numbers, that if I go in there and I pick a number, I'm guaranteed that it's going to be a fraction. Vote, yes, I agree. Or no, I disagree. Can't vote for both. You're yes? Oh, okay, so we have a 100% unanimous? Okay, you're all wrong. All right? And here's why, okay? So we're coming up with numbers, right? We're trying to figure out, like, does this get us everything, right? This with the fractions, is that everything? Is that everything? And then it was proven that there are numbers on this number line that cannot be represented as fractions. I'll give you an example of one. First, let me show you that we actually would need it. Have we all seen the Pythagorean identity? A, B, C, right triangle, a squared plus b squared is c squared. Right? That was proved a long, long time ago. Okay, so if I draw a right triangle, and this is 1 and 1, then what's the hypotenuse? This side would be, let's see, it's c, right? It's 1 squared plus 1 squared equals c squared. So take the square root of 2. So c is root 2. You can prove, and it's not easy. It's beyond the scope of this class, okay? It's something I did in a junior level math class in a course called Foundations of Analysis, where you actually prove that the square root of 2 is not a rational number. It is not a fraction. It's impossible to represent the square root of 2 as a fraction. You're familiar with others. Pi. You've heard of pi before? Pi is an irrational number. There's no way to represent it as a fraction. Now, you may have heard 22 over 7. Anyone ever hear 22 over 7 for pi? That's an approximation, but that's not pi. Another number that you may have heard of is e. Okay, e is that weird number. It's approximately 2.718. So it turns out that if you look at the number line and you put just the fractions on there, there's a bunch of gaps. All the things that are missing are called the irrational numbers, and you cannot represent them as fractions. So we had to throw those into the bag. All right? So now we've got everything now. Okay? If you draw a number line and you put all the fractions in there and you throw in all the irrational numbers, then you have a solid line. And we thought that was enough, and we thought that's all we needed. And then we realized that there are times where we actually get this to happen. And we believed for a long time that there wasn't a reason to really go after this, right? You need someone? Okay, you go. We thought for a long time there's no reason to go after this because it just doesn't make sense. For those of you who are familiar with parabolas, if you have a parabola that goes like this, parabola is a quadratic, that it does not hit the x-axis, so it's never equal to 0. In this case, this is the case where if you try to use the quadratic formula, you get a negative under the root. And so it makes sense visually. Look, you're trying to make me get the square root of a negative number, but look, my graph never hits. And so for a very, very long time, this whole concept, mathematicians just said, we don't need to deal with it. It's not, we don't need it. And then a mathematician came in and proved that for a cubic function, there is a formula like the quadratic function. But for cubic functions, this quadratic formula, the function for the cubic, sorry, you would get square roots of -1. But with all cubic functions, you must have an x-intercept. So we had to be able to figure this out. And so someone came in and said, we'll define it as I. And then the whole thing blew up. And we determined that it works. And that's a whole different field of mathematics. It's called complex variables. And any math majors in here? Are there any? I think there's like 1 or 2. Okay. So the way it works is that what we do in a class like this is we just real quick, imagine it's like a window, right? We just open the window for a second, we go look in, see imaginary numbers, and we close it and we say you're not allowed to look anymore. What you have to do before you study these deep is you have to do college algebra, you have to do calculus, 1, 2, 3, you have to do linear algebra, you have to do, what am I missing here? Yeah, differential equations, diff-EQ. And at this point, you can probably get into a class called complex variables after you've done that. And then you can start studying it. And the reason why I'm going way off track here, the reason why, okay, what I'm trying to do, everyone, is explain to you that you've been living in a fishbowl, all right? Have you ever seen a fishbowl? You got this little fish in there. That fish believes that the entire universe exists within that bowl. You could also, think of it like a fish in a lake, right? Does the lake know that there is a goat living on the mountain? Did I say the lake?
Yeah.
Okay. Does the fish know that there is a goat that lives on a mountain? No. I mean, the fish believes that its universe exists right there. I mean, that's all it knows, right? That's all it knows. And so all you've ever known in your life are the real numbers. Someone has told you about these imaginary numbers. This is the symbol for all real numbers. So this is your fishbowl, but I'm here to tell you that the real numbers actually belong to a bigger place called the complex numbers. So every real number is actually a complex number. All right? Every real number belongs to this bigger system. But not every complex number lives in the fishbowl. So I'm going to give you an example of the sheep, 2 plus I. That is what we call a complex number. It's not real. It's complex. But the math that you can do with this is brilliant. I mean, it is amazing what you can do. If you take off your real goggles and you put on your complex goggles, you can make problems that are very difficult to do here. They turn into very easy problems here, and then you take that answer and you spit it back in here, and it's very simple. You just have to trust me. I'm speaking most to the math people here that the imaginary thing, when we say imaginary, everyone says that's bullshit, it's bogus, like who cares? Like my imaginary friend on my shoulder, everyone thinks I'm crazy. So it got a bad name to start, but it is just as real as every number you've ever dealt with. And it's just as useful. Okay. I think I'll shut up now. Anything else off that packet? Anything else off the packet? All right, let's continue to review then there were those sections in the book, right? R2, R4, R2, R4, R7, R8. So we did a couple of things from R2. Who has not gone outside yet? Just show of hands. Okay. Gone outside to talk with them? Okay, just a few. All right. Just want to see where we are. Okay, quick thing about scientific notation. If I write the number 3765271, this is what we refer to as like standard notation. we like to be able to convert this into scientific notation. So scientific notation, all it does is it takes use of the fact that we are in the base 10 number system. There is a decimal point written here that we normally don't write, correct? And so what I can do is if I multiply this by 10, what happens to that decimal place? Which way does it move? Moves to the right one time? Left one time. I'm multiplying by 10. It's going to go to the right. What if I divide by 10? It goes to the left, right? Yes? So it depends on if I multiply or divide. That all I'm trying to get you to see is that decimal place will move along here if I multiply or divide by 10. Right? It'll dictate that. So what we do is we say, all right, this can be rewritten by moving the decimal place all the way over, right? 1, 2, 3, 4, 5, 6 places to the 3, right behind the 3. Right? These numbers are not the same. So to turn this one back into that one, I would have to move this decimal 1, 2, 3, 4, 5, 6 times. Yes? So that means I have to multiply it times 10 6 times. And so we write, okay, I need to multiply it by 10 times 10 times 10 times 10 6 times, but instead we write to the 6th power. Yes?
Why?
Why what?
Why?
Okay, why? Yeah, this is a good question. Why? Why do we like scientific notation?
For that number specifically, it takes up like more room.
Okay, no, this is a great question. I probably asked the same thing. The reason why is we call it scientific notation also is because it's used in the sciences a lot. So imagine that I want to do some arithmetic on this, and I have a number that's maybe 16 digits, 16, 10 to the 16, very, very long number. If I put something like this and I add to it, like what if I were to add to this, or what if I want to multiply? Multiply is even better. What if I take 4, 7, 9, 2, 5, and I want to multiply these two together? Yes? Then how big is that number? Give me an idea of how big that number is. Well, let's take 3.7, let's convert that one over, 4.7925 times 10 to the what? So I'd have to go 1, 2, 3, 4, so 4. All right, so forgetting this for a second, well, let's look at it now. What's about 4 times about 5? What's this times this? About 20. It's about 20 maybe? This is approximately 20 here. And then what's 10 to the 6th times 10 to the 4th? 10 to the, what do you do to these exponents? You add them? You add them up. Because you're doing 10 to the 6th times 10 to the 4th. Same base, add the exponent. So 10 to the 10th? One more thing. This is a 20 now, right? So couldn't I write this as 2.0 times 10 to the 11th? Yes? So I'm trying to get an idea of the magnitude of this number, right? How big is this number? It's about a 2 with 11 zeros past it. And it becomes easier for us in sciences to deal with this part and get an idea of bigness and smallness. It's just another notation. At the end of the day, you just type in your calculator, you get the number, and you could leave it like this, right? But you also get these significant digits, like how far out do we actually need to go? Do we need all this or not? Or can we just focus on the first 2 digits? So, okay, so I'll let you mess with that. Y'all sound like y'all are pretty comfortable with it. How about this? Converting some words into a formula. The volume of a sphere is 4/3 times pi times the cube of its radius. This, by the way, is number 141 in the book.